review the washer method. Our objective today is to write a definite integral that gives the volume of a solid of revolution that is obtained by revolving a region in the xy plane about a specified axis of revolution. So we've seen the disk method, and today we're going to go on to the washer method. So we've already seen the development of the disk method from the pre-calculus formula for finding the volume of a right circular cylinder or a disk. Volume is equal to the area of the base, which is a circle, so you have pi r squared multiplied by the height. So yesterday we saw the development of the disk method from this pre-calculus formula. We began by approximating the volume of our region by using several disks to approximate our solid, found the volume of each cylinder or each disk, added the volumes of the individual disks, and we got a Riemann sum. And to make our approximation better, we increased the number of disks that we're using to approximate our solid, and we took the limit of this Riemann sum as the number of disks approached infinity. And that limit gave us a definite integral, the disk method formula, the disk method integration formula, which by definition gives the exact volume of a solid of revolution. So what is the washer method, and how does it relate to the disk method? The development follows the same process that I just described, but the only difference is this. When you use the washer method, you use it when you have a solid of revolution that has a hole in the middle. There is a part that's hollow, and basically for each approximating element you will have something called a washer, which is basically a disk that is missing a part of itself, and the part that it is missing is also a disk. So you basically have this. You have, for the volume of a washer, the volume of the disk with no missing part, and then you subtract from that the volume of the missing part, the hollow part, which is also a disk. So they have the same formula for volume. And if you look at the drawing here, the blue part of the drawing signifies the original disk with no missing part, no hollow part. And the green part of the drawing signifies the hollow part or the missing part, which is also a disk. And both disks have the same center. So how do you find the volume of the original disk, the blue disk? Same as what you did yesterday for the disk method, pi r squared. Now, we will now have two radii to talk about. The radius from the center to the outside edge of our washer, and that would give us the volume of the disk, assuming that there's no hollow part in the middle. And then from that we have to subtract the volume of the part that we're missing, the hollow part, which is also a disk. But the distance from the axis of revolution, or the center of the disk to the inside edge, would be designated by lower r, because this is smaller than uppercase R, which measures the distance from the center to the outside of the washer, and lowercase r measures the distance from the center to the inside part of the washer, so that we can find the volume of the missing part, which is also a disk. So that's what we have here, pi times lowercase r squared times height. And look at how we algebraically manipulate this formula. In these two terms, we have a common factor of pi and h. So we factor out pi and h from each term, and this is what we're left with, r squared minus lowercase r squared. And then multiplication is commutative, so I have three factors here, pi h and r squared minus lowercase r squared. So I can just rearrange the order of the factors. And from this pre-calculus formula for the volume of a washer, we have the washer method. Volume is equal to pi times the definite integral from a to b of uppercase r of x squared minus lowercase r of x squared integration with respect to x. Today we want to look at 4 examples. We're going to take the region bounded by the graphs of y is equal to square root of x, y is equal to 0, and x is equal to 9. And in part A, we're going to take that region and revolve it about the horizontal line y is equal to -2. So this is what we have. We have our region shaded green. We have our axis of revolution shown in dashed red, and we're going to take that region in the xy plane and revolve it about the line y is equal to -2. So what we should do is we should begin by drawing a representative rectangle in our region. And what do we get when we revolve this representative rectangle about our axis of revolution? We'll get a washer. So here we're going to take a look at a geometer's sketchpad drawing. So we're taking that region, we're taking a representative rectangle from the region, and we're starting to revolve it about our axis of revolution. Actually, this is not the correct axis of revolution. This is the x-axis as the axis of revolution. So let me show you the correct picture. Okay, so here's a correct picture. The axis of revolution is y is equal to -2. We have our representative rectangle at the right end of the region rather than in the middle, but the idea is the same whether you have one in the middle, at the right end of the region, or closer to the left end of the region. You're going to take each representative rectangle and revolve it about the horizontal line y is equal to -2, and each one will give you a washer. And here we have a series of pictures from Geometer's Sketchpad to help us visualize our washer forming. So you can see our rectangle, it's going behind the x-axis and it's doing the revolution. In this picture, it's completed about half the revolution. So here it's completed about maybe 3/4 of the revolution. And here it's completed the full revolution, and you can see that what we get is a washer. And of course you can see that this here is the part that we're missing. This is the part that we're missing, and this is the what would be a disk if we went missing any part of it. So here's taking another representative rectangle from our region, and if we revolve that representative rectangle about our region, we will get a washer. And you can see that this washer, just like the one that we looked at now, we have the disk, and then besides the disk, we have the smaller disk signifying the part that we're missing. So that's why we have to use the washer method, because we have that hollow part in the middle in our solid of revolution. So this is what we're looking at, and we need to find, for the washer method, we need uppercase r of x and lowercase r of x. They have to be functions of x because, as we understand, our representative rectangle that we began with could have been the one that I drew here. It could have been at the right end of our region. It could have been closer to the left end of our region. So our representative rectangles that we draw in our region to revolve to get our washers, they start at x is equal to 0 and they end at x is equal to 9. In fact, those would be our limits of integration. And why are we going to integrate with respect to x in this problem? Because in the development of the disk method yesterday and in the washer method as well, the dx represents the height of each disk or each washer. And the height of our washer here is a difference in 2x coordinates. the difference in the x coordinates of consecutive partition points. So that's why we have integration with respect to x, because the height of our washer is a difference in the consecutive x coordinates from our partition points, in a pair of consecutive x coordinates from our partition points. So that's why we have integration with respect to x. So you should go through a series of questions when you're deciding how you should write a definite integral to find the volume of a solid of revolution. These are the 4 questions that you need to ask when you're thinking about a solid of revolution. The first question is, should you use the disk method or the washer method? The second question is, should you integrate with respect to x or with respect to y? The third question is, what should be the limits of integration? And the last question is, what should the integrand be? To answer the first question, you draw a representative rectangle in your region, and you visualize it being revolved about your axis of revolution. If there is a hollow part, a part that you're missing, you would use the washer method. And that's what we have to do for this problem. If there is no hollow part in your solid, then you would use the disk method. To answer the second question, you have to look at the orientation of either your washer or your disk. In this problem, look at how the washer is oriented. The height of your washer is a difference in the x coordinates of 2 consecutive partition points. And because it's a difference in x coordinates, you would integrate with respect to x because the height is given by delta x, or delta x sub I, for the width of the ith subinterval of our partition on which our washer is formed. The next question is, what should the limits of integration be? We've already mentioned this. Your region starts at x is equal to 0 and it ends at x is equal to 9. You can have your first washer starting at x is equal to 0 and go to the right until you get to the last washer, which will be at x is equal to 9. So the limits of integration here are from 0 to 9 for x. And the last thing that you need is the integrand. And we're going to look at that next. But the one thing that I want to say right now is this. When you integrate with respect to x, the limits of integration are x values, and your integrand is a function of x. So you actually will have 2 functions of x, uppercase r of x, and you'll square that. You'll have lowercase r of x, you'll square that, and you'll subtract them. So let's take a look at the last part, how to write the integrand for this problem. Here is what you're going to do to write the integrand correctly. So you need 2 functions of x, one for the outer radius of each washer, the distance from the axis of revolution to the outside edge of the washer, and one for lowercase r of x, the distance from the axis of revolution to the inside edge of each washer. So I will now go ahead and draw the vertical line segment from the axis of revolution to the outside edge of an arbitrary washer. So there it is in blue. And I want to find the length of this vertical line segment. To do so, I label the coordinates of the top and the bottom endpoints of my vertical line segment. And as we remember from a previous lesson, to find the length of a vertical line segment, you subtract the y coordinates of the top and the bottom endpoints. So what is uppercase r of x? It is the square root of x minus negative 2, or if you simplify, you get the square root of x minus negative 2 is plus 2. So that's our function uppercase r of x. And we're going to take that and substitute it for uppercase r of x in the washer method formula, the integration formula for the washer method. And now we need to find lowercase r of x. So now observe as I draw a vertical line segment from the axis of revolution to the inside edge of each washer. So here's my vertical line segment in yellow, and I want to find the length of this vertical line segment. So how do I do that? I need to label the coordinates of the top and the bottom endpoints. So I already have the coordinates of the bottom endpoint from earlier. X negative 2, and the coordinates of the top endpoint will be x0. Why is it negative 2 for y for the bottom endpoint? Because it's on the horizontal line, y is equal to negative 2. Why is it x0 for the top endpoint? Because it's on the horizontal line, y is equal to 0. So now to find the length of this vertical line segment, we do what we learned earlier. We need to subtract the y coordinates of the top and the bottom endpoints. So we're going to have 0 minus negative 2. So 0 minus negative 2, it simplifies to 2. So that's lowercase r of x. So now we're going to take that and we're going to substitute that in the integration formula for the washer method. So here's the definite integral that will give the volume of this solid of revolution. We have the washer method, and we're going to integrate with respect to x. The limits of integration are from 0 to 9. So we write pi times the definite integral from 0 to 9. And now I know uppercase R of x is square root of x plus 2. I need to square that, and I need to subtract from that lowercase r of x, which I know is 2. I need to square that, so I have this and integration with respect to x. So we've written the definite integral. If you want to evaluate it, make sure you square root of x plus 2 first, and then you square 2, and then you subtract. And of course, you would continue with the fundamental theorem of calculus. Let's move on to part B, where we take the same region, but now we're going to revolve it about the horizontal line, y is equal to 4. So again, we need to go through our 4 questions. Should we use the disk method or the washer method to find the volume of this solid of revolution? When we take the region bounded by the graphs of y is equal to square root of x is equal to 9, and y is equal to 0, and revolve it about the horizontal line, y is equal to 4. So to answer the first question, what we should do is we should begin by drawing a representative rectangle in our region. And then you should visualize it being revolved about our axis of revolution. And what does it give us? It'll give us a washer. There's a part that's going to be missing, the hollow part, so it's going to give us a washer. So we need to use the washer method. Should we integrate with respect to x or with respect to y? If you look at our washer, the height of our washer is a difference in the x coordinates of consecutive partition points. So it is delta x sub I, so we should integrate with respect to x. What should be the limits of integration? Our first washer will start at x is equal to 0, and our last washer will end at x is equal to 9. So our limits of integration would be from 0 to 9. And finally, what should be the integrand? So for the integrand, we need uppercase r of x and lowercase r of x. What is uppercase r of x? It's the distance from the axis of revolution to the outside edge of the washer, and lowercase r of x is the distance from the axis of revolution to the inside edge of the washer. So we're going to find uppercase r of x. It's the distance from the axis of revolution to the outside edge of the washer. You can see that's going to be given by the length of this red line segment. So I need to label the coordinates of the top and the bottom endpoints for this vertical line segment. The top endpoint is on the axis of revolution, where y is equal to 4, so I have the coordinates x4. And the bottom endpoint is at the bottom of our region, which is bounded by the graphs of y is equal to square root of x, y is equal to 0, and x is equal to 9. So the bottom endpoint is on the line y is equal to 0. So what is uppercase r of x? It's the length of this arbitrary vertical line segment, and it's 4 minus 0. So no matter where you draw this vertical line segment, from the axis of revolution to the outside edge of your washer, it's always going to be a constant 4 for uppercase R for this problem. So what about lowercase r of x, the distance from the axis of revolution to the inside edge of the washer? So I'm going to draw a segment in green. And again, it's an arbitrary vertical line segment between the axis of revolution and the inside edge of the washer. So depending on where you draw the line segment, it will have different lengths, as you can see from the several that I've drawn here. So it's a function of x for that reason. And to find the length of an arbitrary vertical line segment between the axis of revolution and the inside edge of a washer, you're going to have to label the coordinates of the top and the bottom endpoints. We've already labeled the coordinates of the top endpoint. It's on the axis of revolution. We did that earlier. And now we're going to label the coordinates of the bottom endpoint, which is right here. And this endpoint is on the graph of y is equal to square root of x. So it will have coordinates x, comma, square root of x. So what are you going to do to find lowercase r of x? Lowercase r of x is going to be the length of this vertical line segment, top minus bottom. And to do top minus bottom, you're going to have 4 minus square root of x. So that's lowercase r of x. So we saw that uppercase r of x was a constant in this function, but lowercase r of x is a function of x. We saw that uppercase r of x was a constant in this problem, but lowercase r of x is a function of x in this problem because depending on where you draw the washer, the inside radius could be longer or shorter. So now we're ready to write our definite integral to find the volume of this solid of revolution. So let's write our definite integral. Volume is equal to pi times the definite integral from 0 to 9. Uppercase r of x, we just found that to be 4, so we'll have 4 squared minus lowercase r of x squared, which is lowercase r of x was found to be 4 minus square root of x. So now we'll take that quantity and square it and put all of that in parentheses, and we have integration with respect to x. So now we go on to our third problem. We take the same region, the region bounded by the graphs of y is equal to square root of x, y is equal to 0, and x is equal to 9. And we're going to revolve this region about the vertical line x is equal to 0, or the y-axis. So we're going to take this region and we're going to revolve it about the y-axis. We want to write a definite integral that will give us the volume of this solid of revolution. So now we're going to go through our series of questions. The first question is, should we use the disk method or the washer method? And how do you answer that first question? Well, you think about the region that you have and your axis of revolution. You can intuitively see that this is going to result in sort of like a bowl-shaped solid. It's going to look something like that. But you're going to take this region and revolve it about the y-axis. So what you need to do to answer the first question, disk or washer method, and also to answer the second question, integration with respect to x or with respect to y, is to be mindful of your region and your axis of revolution and begin by drawing a representative rectangle from your region. After you draw your representative rectangle, visualize it being revolved about the axis of revolution. Does it give you a solid disk, or is there going to be a hollow part, a missing part? Will you get a washer? So you can observe me as I draw what we would get. There is actually a hollow part in the middle, because you can see that there's a gap between the axis of revolution and our representative rectangle, and because of that gap, we're going to have a hollow part in the middle. So we would have to use the washer method for this problem. The next question is, should we be integrating with respect to x or with respect to y? Well, if you look at this washer that we have, the height of our washer is over here. And that's going to be found by subtracting consecutive subtracting a pair of consecutive y coordinates from our partition. So we have delta y sub I. And why do I say our partition? Because if you look at our region, it starts at y is equal to 0 at the very bottom, and it goes all the way to y is equal to 3 at the very top. And to form our individual washers, we have to divide that interval from y is equal to 0 to y is equal to 3 into a number of sub-intervals, and when we do that, we have a partition. So to find the height of an individual washer, you subtract the y coordinates of a consecutive pair of partition points. So that's why we have delta y sub I, and because the height is given by delta y sub I, you would integrate with respect to y. So what would be the limits of integration? You're starting at the very bottom of the region where y is equal to 0. Y is equal to 0 at the very bottom of the region, and you're going to the very top of the region where y is equal to 3. So those are the limits of integration. And finally, what is the integrand? The one thing that I want to say before I get into the details is because we're integrating with respect to y, your integrand must be a function of y. So you have to write uppercase r as a function of y and lowercase r as a function of y. Let's see how we do that. So where is uppercase? Well, how do we find uppercase r of y? It is the length of a line segment drawn from the axis of revolution to the outside edge of each washer. So let's draw a line segment from the axis of revolution, which is x is equal to 0, to the outside edge of this washer that I've drawn here. So I'm drawing it in red now. So it's a horizontal line segment. So how do we find the length of a horizontal line segment? As we learned in a previous lesson, you subtract the x coordinates of the two endpoints, right minus left. So let's label the x coordinates of the two endpoints. The x coordinate of the right endpoint is going to be 9 because it is on the graph of x is equal to 9, and the y coordinate is variable. It could be anywhere from y is equal to 0 to y is equal to 3. And for the left endpoint, the x coordinate is going to be 0 because it's on the graph of x is equal to 0, and the y coordinate is variable. It can be anywhere from 0 to 3. So uppercase r of y, the length of a horizontal line segment, is found by subtracting the x coordinates of the right and the left endpoints. So uppercase r of y is 9 minus 0. In this particular problem, the outer radius is a constant value. It doesn't change regardless of whichever washer you may be looking at within the region. So now let's look at lowercase r of y. Lowercase r of y represents the length of, it represents the distance. It represents the distance from the axis of revolution to the inside edge of each washer. So let me go ahead and draw a line segment to represent the distance from the inside edge, from the axis of revolution to the inside edge of each washer. So it is actually given by this horizontal line segment. The horizontal line segment from the axis of revolution to the inside edge of the washer. And you're going to go ahead and find the length of this horizontal line segment, and to do so you need to label the coordinates of the endpoints. The right endpoint, it's on the graph of y is equal to square root of x. So how would you label the coordinates of the right endpoint? Well, the y coordinate is variable from 0 to 3. The x coordinate, it's on the graph of y is equal to square root of x. So x is equal to y squared. So you're going to write y squared here. And the length of this horizontal line segment is found by subtracting the x coordinates of the two endpoints, right minus left. So we have lowercase r of y is going to be y squared minus 0, or just y squared. It is a function of y because depending on where you draw that horizontal line segment between the axis of revolution and the inside edge of each washer, it'll be different lengths depending on where that is drawn. Now we're ready to write the definite integral because we are now able to write the integrand. So in this problem, we know we have to use the washer method. We know we have to integrate with respect to y. The limits of integration will be from y is equal to 0 to y is equal to 3, from the bottom of our region to the top of our region. And here is our definite integral. Pi times the definite integral from y is equal to 0 to y is equal to 3. And uppercase r of y is 9, so we have 9 squared minus lowercase r of y is y squared minus 0, or just y squared. So we have y squared squared, and then integration with respect to y. And there's our definite integral for the volume of the solid of revolution obtained by taking our region and revolving it about the vertical line x is equal to 0. So in this problem, we're going to take our region and we're going to revolve it about the vertical axis of revolution x is equal to 10. It's the same region that we've been looking at, the region bounded by the graphs of y is equal to square root of x, y is equal to 0, and x is equal to 9. So we go through our 4 questions, disk or washer method. We need to use the washer method. So if you take a representative rectangle and revolve it about the axis of revolution, you see that you get a washer. There's a hollow part, so we need to use the washer method. Should we integrate with respect to x or with respect to y? The height of each washer is found by delta y sub I, so we need to integrate with respect to y. What should be the limits of integration? The limits of integration should be from y is equal to 0, the bottom of our region, to y is equal to 3, the top of our region. And finally, what should the integrand be? Because we're integrating with respect to y, the integrand must be a function of y, and we need something for the outer radius of each washer, uppercase R of y. We need a function of y for that, and a function of y for the inside radius, the distance from the axis of revolution to the inside edge of each washer. So for the uppercase R of y function, we need to find the length of a segment drawn from the axis of revolution to the outside edge of each washer. So here's our axis of revolution. So we're going to draw a line segment from the axis of revolution to the outside edge of each washer. So we start at the axis of revolution and we go to the outside edge of the washer. So that's what we have. So now we're going to label the endpoints. The right endpoint is going to be, it's on the graph of x is equal to 10, so x is 10, and y is variable. It can go from 0 to 3. The left endpoint, the x coordinate will be given by, because this left endpoint is on the graph of y is equal to square root of x is equal to y squared, and the y coordinate is variable. So when you do right minus left of the x coordinates, you get 10 minus y squared for uppercase R of y. And for lowercase r of y, you're going to draw a line segment from the axis of revolution to the inside edge of your washer, and you want to find the length of that line segment. So let's look at that. So here's our axis of revolution, and here's the inside edge of our washer. So here's our line segment from the axis of revolution to the inside edge of the washer, and the right endpoint of this line segment, the coordinates have already been labeled. The left endpoint is going to be It's on the graph of x is equal to 9, so the x coordinate will be 9, and the y coordinate is variable from 0 to 3. So to find the length of this horizontal line segment, you subtract the x coordinates right minus left. 10 minus 9 is 1, and lowercase r of y is 1. So here's our definite integral. Volume is equal to pi times the definite integral from y is equal to 0 to y is equal to 3 of uppercase r of y squared. That's going to be 10 minus y squared squared minus lowercase r of y. Lowercase r of y is 1 squared, and all of that in parentheses and integration with respect to y. So to summarize, we looked at the relationship between the disk method and the Washa method, and we applied the Washa method to find the volumes of 4 solids of revolution. 2, we had integration with respect to x for problems in which we had horizontal axes of revolution, and we looked at 2 other problems where we had integration with respect to y for problems in which we had vertical axes of revolution.